Generation and utilization of electricity has been an area of engineering that is seeing rapid change over the last few years. We all want cleaner sources of energy, and with that requires new technologies to maximize the efficiency of how we generate that energy and use it. New wide bandgap semiconductor materials, silicon carbide and gallium nitride, are enabling new levels of capability in our systems. What is the direction of this technology, and when should we consider this technology in our designs? Whether we're looking at maximizing the efficiency of an inverter or looking at extending the battery life of a robotic system by increasing the efficiency of the H-bridge driving our motors, we as engineers are constantly looking at ways of whether or not we should be transitioning from traditional silicon and power silicon that we've been using for decades now, or if we should be looking at the newer technologies in wide bandgap, silicon carbide and gallium nitride. There's great capabilities in those technologies with much higher switching speed capability, much lower impedances that can be great in our systems, but at what point in a design cycle, in a design definition, should we be looking at these technologies as we do our embedded system designs? Today, I have the privilege of speaking with Hunter Freburg, technical marketing engineer at onsemi, responsible for their power solutions group, and someone who's spent a lot of time with silicon carbide specifically. Hunter, thanks so much for joining me on The Current today.
Thanks for having me, Todd.
Really appreciate it, and really glad to pick your brain on this subject, because I think it's a really important subject that many of us engineers are looking at. With all the benefits in a data sheet that we see with these wide bandgap technologies, but sometimes price tags that can be a little bit, scary in some cases, and that we may say, oh man, it would be a lot cheaper to go with, traditional power silicon. It's a big, decision that we as engineers have to make for our systems. So let's start at the very beginning of wide bandgap technology a little bit, and what, from a production standpoint, has really enabled us to grow the way that we're doing these different semiconductors and start utilizing silicon carbide and gallium nitride technologies.
Right. So for silicon carbide and the devices that onsemi manufactures, we've increased our production in a couple of different ways, mostly coming down to the fortification of our supply chain. So our vertically integrated supply chain, what we call powder to products or substrate to systems. So we manufacture the silicon carbide boules themselves. That's due to our acquisition of GTAT Systems. We do the wafer fabrication. We do in-house packaging. So we handle that entire process, like I said, all the way from the silicon carbide boules and the powder that makes those boules all the way up to the devices and the systems that we incorporate those devices into. And then the other thing is largely going to come down to yield improvements. So through that manufacturing process, we do in-process control and burn-in of our devices, defect scanning, and avalanche testing of all the devices during that manufacturing process. And through kind of refining that process, we've substantially improved the yield on our wafers. And then the other thing to consider too is the advances in the technology. So for us in particular, we have certain generations of MOSFETs and diodes. We're currently on our third generation for silicon carbide. That's our M3 and our D3. But I'll say again, for our MOSFETs, comparing our first generation, our M1 to our M3, the die size is quite a bit smaller. And with that, you can fit more devices onto a single wafer and therefore increase your yield even further. So since the start of COVID, over the last 3 years, we've seen about a 10x increase in our capacity. And we're continuing to try to bolster that to meet the insane demand of the automotive and energy infrastructure markets.
Yeah, that's an incredible capacity increase. And I think, the demand is there. There's a lot of people that want to use it, and we're going to continue to see more industries, I think, leaning on this technology, which is really exciting. We're looking at silicon carbide and using that and bringing that into one of our systems. What do you kind of see as the inflection point from an engineer to make that decision to go to silicon carbide versus using traditional silicon? And what do you see also, it's kind of a follow-up to that, kind of the benefits and downsides of using silicon carbide versus using traditional silicon.
Right. So largely comes down to, say, the material properties of silicon carbide and the benefits that you have over silicon. So the biggest thing that I'm going to mention for high power applications, which is typically where you're going to find these, is an increase in your breakdown voltage and your field robustness. That's about the field robustness or your dielectric breakdown is about 10 times that of silicon with silicon carbide. So it can withstand much higher voltages. It can operate at a lot higher voltages, as I said. And then the other thing is the thermal conductivity of the material. And that's about 3 times higher with silicon carbide as opposed to silicon. So with better thermal conductivity, you have greater heat transfer for a particular area, and therefore your devices can operate at much higher power, higher switching frequencies. And so a thing to consider is that silicon carbide or adopting silicon carbide in your design isn't just changing out that particular transistor, that particular switch. You have to look at the entire system. So with that improvement in thermal conductivity, you'll have smaller heat sinks, you'll have smaller passives and magnetics due to the higher switching frequency, which overall could reduce the size of your system, smaller condenser, more efficient. So it's a pretty big improvement over silicon, opting for silicon carbide for these high power designs.
A few months back, there was a lot of different press releases I saw from, we'll call it a large electric vehicle manufacturer in the U.S. was making some comments that they were going to reduce their reliance on silicon carbide in their battery recharge systems and in their batteries themselves. And I think that caused a lot of panic in the industry that I think was a little bit silly. I think that was just really a headline. I think the reality is that, electric vehicle makers are going to continue to be looking at wide bandgap technologies like silicon carbide significantly. Is that a good read on my side, or do you think that there's any merit to the fact that there may be a reduction in wide bandgap in electric vehicles?
So some of these headlines have been detrimental. They've come out and said that silicon carbide is dead. For these lower power applications, automotive manufacturers are looking at not necessarily incorporating as much silicon carbide into their designs, as you said. But again, it's not, that is technically true, but it's for different reasons than you might expect.
Right.
Largely, it honestly comes down to the performance benefits or the performance enhancements that we've seen with silicon carbide as the technology has matured. So you have things like a reduction in your RDS on or your drain to source resistance while the device is in its on state. You have things like improvements in current capabilities. So some FETs going from like approximately 50 amps on average to even 100 amps or higher, being able to handle that much current. So in your existing designs, you're typically having to parallel many switches on a particular leg so that you can get to lower RDS on to improve your conduction losses or to be able to handle more current. But as, again, these devices are improving, you don't necessarily need to parallel as many devices to get to a similar performance level. So there is a reduction in SiC, but it's largely, again, due to the performance improvements of the devices. So it's kind of beating itself in a way.
Right.
But again, it's not necessarily a concern from the manufacturing standpoint. Like I said, we've increased our capacity substantially, but we don't see that going away. So at a vehicle level, sure, they'll be reducing their silicon carbide device count. Yeah. But overall, if you're reducing the price of your vehicle, the adoption should increase. So the biggest hurdle that we see today in electric vehicles, I would say, is cost, quite honestly, for the consumer. Most consumers are looking at your typical ICE or ICE, your internal combustion engine, and it's far cheaper than the next best electric vehicle option. But again, as you improve affordability, consumer adoption is going to increase drastically and is likely to offset the reduction in silicon carbide devices in your traction inverter application.
Right, right. I think to some extent, the technology, I think you kind of mentioned a little bit, the technology is almost its own worst enemy, because it
Right,
has improved so much, it has gotten so good, and the impedance levels on a silicon carbide MOSFET have gotten so low that you can reduce the number of silicon carbide FETs you're using in a
right,
system, and so it hurts some of that. But to your point, just market forces being what they are, the theory would be that, as the prices of whether we're talking about electric vehicle or the recharge circuit for that, or a silicon carbide motor driver system, as those costs come down, the volume purchased should go up, so volume should continue to
right,
be strong. I don't see this technology going away myself. This isn't truly damaging. It's a slight little road bump in the scheme of things.
right.
So. So, for me as a design engineer, I've been doing this for 22 years now, and if I'm doing my next design, and I've always been doing power silicon, whether we're talking about a solar inverter, or whether we're talking about a motor drive circuit, or whether we're talking about an electric vehicle, whatever it might be,
Mhm.
and I'm going to do my first design where, by gosh, I'm moving over to silicon carbide. What design considerations should I be keeping in mind? Are there differences in doing that circuit versus doing that traditional power silicon circuit?
Right. So there are,
Yeah,
as I kind of mentioned in the beginning, differences between silicon and silicon carbide at that system level, like you referenced. Um, Silicon carbide, you're typically going to opt for it because it's going to allow you to reach higher frequencies, higher efficiency, higher power.
right.
With those higher switching frequencies, it enables you to reduce the size of many of the EMI filters, of your magnetics, um, of the capacitors on your board. So you'll likely need a board spin to integrate that silicon carbide to really get the best benefit from it. Um, I'll also mention again, reduction in the size of your heat sinks, that better thermal conductivity. Your designs don't necessarily need to be as bulky because of one really, really big chunk of aluminum. You can bring that down and your design becomes more dense and more thermally efficient. But I will say that one of the biggest considerations between silicon carbide and silicon designs is going to be the gate drive voltage for these devices. So it's quite a bit different for silicon carbide versus silicon. Your typical silicon gate drives voltages are going to be like 0 to 10 volts, 0 to 12 volts. But with silicon carbide, we go quite a bit higher than that. And we actually go negative for your off-state voltage. So for our current M3 devices or our third generation MOSFETs, their recommended gate drive voltages are positive 18 volts and negative 3 volts. Um, so there are some design challenges there as far as how to um, drive the gates of these FETs.
Yeah,
But I'll speak to as far as the improvements are concerned and why we have these different voltage levels or these non-standard, not typical gate drive voltages. It's because of the improvements in conduction losses and switching losses. So our current third generation, like I said, um, they can operate from 0 to 15, so close to that silicon carbide or silicon gate drive level. But if you go, for instance, from 15 volts to 18 volts for that, the voltage that's required for the device when it's on, you're going to improve your conduction losses by 25% and your turn on switching losses by 25%. And then going from 0 volts to negative 3 volts, you'll actually improve your turn off losses by 25% as well.
right.
So running at these non-standard as compared to silicon gate drive voltages, you see substantial performance improvements in the device.
Right, right. Very nice. So there are some complexities you got to take into consideration when you're doing the design, but nothing I think that's insurmountable, and nothing that should be, too terribly out of the ordinary for any of us that have done a power circuit before.
Right.
So, obviously this is a hot area of technologies we've talked about. Obviously onsemi's increased your capacity tremendously when it comes to silicon carbide, but there are a lot of other players out there in this space. From your perspective, where do you see onsemi really outperforming other vendors when it comes to silicon carbide and this technology overall? And why should an embedded engineer choose the onsemi solution versus others?
Right. Great question. So for our place in the market and where we outperform our competitors, I think comes down to, again, our vertically integrated supply chain, so that that oversight of the entire logistics chain of the entire process really gives us confidence that we can move things along if there's any hiccups and there's not trying to coordinate with multiple suppliers for multiple different things. We handle everything. Like I said, from the full manufacturing to in-house packaging to wafer fabrication, device fabrication, we do it all. Um, I'll also mention that the improvements in our technology are um, continuing to trend towards better, more efficient devices. Like I said, lower RDS on, so implementing new techniques and just innovating and developing new devices that are better for higher temperature operation, lower parasitic capacitances, little to no reverse recovery charge with our latest third generation, for instance, and continuing to improve upon those devices with the coming fourth, fifth generation devices. And then the last thing I'll mention is actually our support for our design tools. So we have a wealth of information for DC fast chargers, for onboard chargers in different power levels, 25 kilowatt. We have a 120 kilowatt design coming for a DC fast charger that incorporates some of our half bridge modules. We have a 6.6 kilowatt and a coming 11.2 kilowatt onboard charger. These systems are both bidirectional, so they incorporate that functionality into the chargers. So lots of resources out there and support for engineers. And then the last thing I'll mention around the design tools is actually our simulation tools. So we have physical and scalable models, which I'm sure many people have heard us talk about a lot, but what exactly that means and how they're different from our competitors. So in a traditional case, you're going to build your device, test your device, and then you're going to backfill those parameters into a data sheet. But the problem is that when you're testing those devices, it's in the real world, you're on a board, and you have to account for all of the devices that are in that circuit when calculating your efficiency overall. Whereas with our models, they're actually based on the structure of the device itself. So it's not empirical, or the data sheets aren't empirical in nature. Per se, the actual models are, again, based off of the actual architecture of the silicon carbide devices themselves. So they're quite a bit more sophisticated than some of our other competitors. And then in addition, we have SPICE models for these Plex. We have our new Elite SIC simulator tool that you can go online and have over 30 different topologies to choose from, different applications, whether industrial and automotive, and you can run thermal and electrical analysis for these devices. For something that would be a $100,000 license for you to buy yourself, we offer it for free on our website. We do the simulations from our server, so it's not intensive on your machine or your computer to run these simulations. So overall, it's a tremendous benefit to customers in maybe not having to do as many prototypes and board spins to really maximize and optimize the efficiency that you're looking for.
Right. Well, definitely a lot of great benefits there, and we're seeing that within engineers that are looking at silicon carbide technology, where onsemi is certainly a strong player and has some great products out there that are absolutely worth taking a look at. And Hunter, thanks so much for taking the time to discuss this important topic with me today. This is, I think, wide bandgap's been around for a little while, and I think it's starting to get some maturity underneath it, but it still is, I think, a fascinating area of technology that's really going to allow us as engineers to do a lot of new cool things with our designs in the decade to come. So really appreciate you spending a little bit of time talking about the direction that onsemi has taken that. Thanks also to our viewers so much for joining us on this episode of The Current. If you have any questions about designs that you might be doing, looking at silicon carbide or any other wide bandgap technologies, we would love to have our engineers make introductions with onsemi's engineers to help you with those designs, help you make the right decisions and move forward. Also, for any other embedded needs that you might have, Future Electronics is here to assist you. And we look forward to seeing you on the next episode of The Current. If you do have any of those needs, please do reach out to us at Shaping the Future. Again, that's one word, Shaping the Future, at futureelectronics.com. Thanks so much for your time, and we'll see you on the next episode of The Current.